All right, so today I want to pick up where we left off with equilibrium yesterday. Hopefully you were able to make sense of the ideas related to equilibrium. And so we're going to start today by looking at the graphs of systems that are experiencing or attaining equilibrium. So remember that an equilibrium system is a system where what you're going to see is the reaction may be proceeding after a period of time in both the forward and the reverse direction. And so after a certain amount of time, macroscopically what we're going to see is we're going to see constant amounts of both reactants and products. And so we may be able to indicate that by looking at the relative color of the reaction mixture or the pressure or a variety of other methods to identify whether the system is indeed established an equilibrium. But keep in mind that just because a system is in equilibrium does not mean that necessarily the amount or the concentrations of reactants and products are necessarily equal, although they can be. So let's take a look at the graph, this graph right here. So I can tell that my N2O4 is going to be a reactant in this reaction because its quantity, initial quantity, is not 0. And so I'm starting off with 0 NO2 based on this particular scenario. And so as you can see, over time, the amount of N2O4 is decreasing. Why is it decreasing? Because this N2O4 is going to be reacting, the forward reaction is going to be proceeding, and that's going to create some NO2, but it's going to consume our N2O4. And so the amount of N2O4 is decreasing over time. As you would expect, if the N2O4 is being consumed, it's being consumed so as to produce NO2. And so the amount of NO2 we see steadily increasing over time. And so when do we see equilibrium having been established? Well, the point in the graph where you see that the concentrations are remaining relatively stable is the time at which equilibrium has been established. And the concentrations, where these level out, are the equilibrium concentrations. Now, if we were to change certain variables within within this circumstance, then we may see a shift again, and a new equilibrium might be established. So some other possibilities. I just want to talk about this because I think it's important to discuss. So I'm just going to set up a couple of different graphs here, and again we're going to have time and concentration versus time for both of these graphs. And so in this particular circumstance, I can see that the equilibrium concentration of N2O4 is still higher than the equilibrium concentration of NO2. So in this circumstance, we can say that this reaction favors our reactants because we still have a higher amount of reactant at the end of the reaction once this equilibrium has been established relative to the amount of NO2. And so this reaction would have gone less than 50%. Now let's talk about what a graph would look like. The graph would look like if the reaction instead favored our products. So I want you to visualize for a minute, maybe try this on your own and see what you would expect of this graph. All right, so let's go through it. So I'm going to use the same color code as I have in my original graph here. If my amount of N2O4 were less than the amount of NO2, that would indicate that the reaction favored my products. So I would look at it and I would start, okay, well, it's going to go down and level off, same as before. But the difference between my new graph and the original graph is that the final concentration of my NO2 is going to be higher than that of my N2O4. Here's another scenario for you to consider. Although in neither of these circumstances are the concentrations of reactants and products equal, that is definitely a possibility in certain equilibrium systems, although it's not necessarily the case. So I want you to think about, well, what would the graph of an equilibrium system where the products and reactants were in equal quantities, what would that look like? Well, hopefully you had what you envisioned looked something like this, where at some point those reactants and products are going to align themselves and be parallel to each other so that the amount at equilibrium, the concentrations, if that's how we're measuring amount, will be the same. All right, so let's step into the second topic today, which is percent reaction. So percent reaction really just describes what quantity of products we have in the reaction compared to if that reaction were to go to completion. So for example, I know if, based on what we would have known from grade 11 chemistry, if this reaction of H2 plus Br2 were to go to completion, then whatever amounts of H2 and Br2 I started with, I would use mole ratios in order to determine the amount stoichiometrically of HBr that could be produced. However, in our grade 12 more mature version of stoichiometry, we know that any equilibrium system may not necessarily go to completion. In fact, we know that it often will go in the reverse direction before the reaction is complete. So not all reactants are necessarily converted into products. And so in that circumstance, it may be helpful for the chemist to know what the percent reaction is, and so that you know whether the reaction is financially viable or is just practically workable. There are all sorts of reasons why you might want to know the percent reaction in a given equilibrium system. So let's start out with a simple example, remembering, of course, that the percent reaction is we're measuring how much HBr was made relative to the amount in an optimal circumstance where the reaction were to go to completion. So let's read through the question. It says, the reaction begins with 1 mole per liter of each reactant and no products. Okay, the system is allowed to reach equilibrium, at which point the concentration of HBr is found to be 1.05 moles per liter. What is the percent reaction? All right, so let's take a minute to just make sense of this. So I know that the percent reaction is equal to the actual amount. In this case, we're going to use concentration, divided by the theoretical or possible concentration if the reaction were going to completion divided or times 100. So the actual amount, the actual concentration is easy. They give that to us. They tell us at equilibrium, that's the concentration of HBr and they tell us that's 1.05 moles per liter. Now, to get the possible amount of HBr that is produced, we're going to use our mole ratios. So let's take a look at how we would calculate the possible amount of HBr produced. So when I look at this reaction, I know that I'm starting with 1.00 moles per liter of both of my reactants here, 1.00 moles per liter. And so if I look at my mole ratio, I can see that the coefficient in front of each of these reactants is 1. And my mole ratio is 1 to 2, which means that for every 1 mole of Br2 or H2 produced, I'm going to produce 2 moles of HBr. And so the math here is actually quite simple. And so that tells me that I am going to be, in theory, if this reaction goes to completion, going to be producing 2.00 moles per liter. Right? But let's just in case a situation arises where the mole ratios aren't as convenient as this, let's see how we would work that out. Well, I know that I have 1.00 mole per liter of H2. I'm going to use H2 in this circumstance. but I don't want moles of H2. I want moles of HBr. So I need to cancel out my moles of H2, and I need to keep moles of HBr. And so I know that for every 2 moles of HBr that are produced, I'm going to use 1 mole of H2. And so dimensionally speaking, my moles of H2 are going to cancel, and my 1 mole per liter times 2 moles for every 1 mole will give me 2 moles per liter of my product, in theory. So now let's carry on with this question then, because now that I know that my possible amount, that was this 2 moles per liter, right over here. That's my possible amount. So that my percent reaction is going to be the 1.05 moles per liter that I did produce versus the 2 moles per liter that I could have produced times 100. And so that gives me 52.5%. So I'm going to write that out, 52.5% to 3 sig figs. And when I look at this answer, you know, this tells me that this reaction actually slightly favors my products. Why? Because the percentage is greater than 50%. Hopefully that made sense to you. If you have any questions, be sure to reserve them for our next class together. So now I want to introduce you to a fundamental tool for solving equilibrium problems, and that is the icebox. So the icebox is, ICE is an acronym for the various components or concentrations that you're going to need to consider when you're working through an equilibrium problem. So I in ICE stands for initial. So initial what? Initial concentration. So I can be talking about the initial concentration of my reactants or my products. And then I want to consider how those initial concentrations change as the system proceeds towards equilibrium. That's the C in ICE. And then lastly, equilibrium concentration. So that describes, you know, the final equilibrium concentrations once that equilibrium has been established. So I want to talk to you a little bit about some of the basic rules related to using an icebox. So first off, I'm just completely making up some values here, just for example's sake. So they're not meaningful in any kind of real question situation. So, but most often than not, we'll start with a certain amount of our reactants and then none of our products. So usually, in most cases, when we're first starting out, the initial amount of my product will be 0 moles per liter. Why? Well, I haven't made any. At the beginning of the reaction, I usually will only have reactants present. So I'm just going to, you know, just for argument's sake, just make up values of, let's say, 1.0 moles per liter for each of these reactants. So any change that we observe is going to involve considering mole ratios, right? Remember that our chemical reaction is really just a recipe in order to make certain products. And so the changes that are going to happen are going to consider what the mole ratios are in the given reaction. So I know, for instance, that if I experience a decrease in one reactant, I'm going to just say, you know, by a certain amount X, then I know my other reactant is going to have to decrease as well. Okay, reactants react together, so they're either both increasing or both decreasing. In this case, they're decreasing in quantity because they're getting used up to make products. And so I know that if N2 with a coefficient of 1 decreases by 1x, then my hydrogen concentration will have to decrease by 3 times as much, so 3x. So then looking over to my product and how it's going to change, if my reactants are getting consumed, right, they're decreasing, then any of the, you know, those molecules and atoms, those bonds are breaking to form my product. And so I'm going to expect an increase in my product. And again, we're going to consider mole ratios here, so it's going to increase by 2x. And so how do I get my equilibrium concentration? Well, I get that by combining my initial and my change. So initial plus change equals equilibrium. So I can, at this point, because I don't know the value of x, I could write out an expression to describe the equilibrium concentrations, and maybe at a later point I will have enough information to solve for x. So right now I would just write out as 1.00 minus x, 1.00 minus 3x, and then simply 2x. So again, I'm getting those equilibrium concentrations by saying my initial plus my change equals my equilibrium concentration. So for your own notes, please write down the following rules. As we just discussed them, we're going to use mole ratios in order to determine the changes in concentration. All reactants will change in the same direction. In other words, they're all going to increase or they're all going to decrease in concentration. And lastly, all products are going to change in the opposite direction to the reactants. Because if the reactants are going to decrease, then we're going to expect the amount of our products to increase, and vice versa. All right, so let's look at a second example here. So in this example, we're taking some ammonia and we're going to be heating it. And when we heat it, it produces these products, so we can see that it's an equilibrium system. And they're telling us that when 4 moles of ammonia is introduced into a 2-liter container and heated, the amount of ammonia shown in the graph below results. So I'm going to take a look at this graph here, and I see that, equilibrium is established around this point, and I trace that back, and it looks like I can pretty confidently say that that's happening. There's about 2 moles present of ammonia when the system reaches equilibrium. And so the question down here is saying determine the equilibrium concentrations of the other 2 entities, then sketch their amounts on the graph above. All right, so a couple things that I need to be aware of here. This question is saying that I have 4 moles, but it's not 4 moles in a liter, it's 4 moles in 2 liters. So I want to look carefully at my graph and remember that this graph is not graphing concentration versus time, it's looking at amount in moles versus time. So that's something to consider. All right, so let's practice doing our icebox. So set up an icebox for yourself. I'm going to do that right here on the side. So start by writing out my reaction equation here. 2 NH3s reacting to make an N2 and an H2, 3 H2s rather. And just to simplify things, I'm not going to include units. We're going to assume some units, but it is good form to include those units in as a side note. All right, so some work on the side here. I know that I have my 4 moles, my initial 4 moles of ammonia in 2 liters. So I'm going to do a quick calculation here on the side. I know that I have 4 moles of ammonia in 2 liters, which tells me that initially I have 2 moles per liter of ammonia. So I'm going to put that into my ice chart. And so I have none of either of my reactants, so I'm going to just put that in as my initial concentrations, put 0 in as my initial concentrations. And so I don't know by how much my ammonia is going to decrease, but I know it's going to decrease by an amount 2x, and I've yet to figure that out. And so that means that the amount of ammonia is going to increase by x, or sorry, nitrogen rather, is going to increase by x, and the amount of hydrogen is going to increase by 3x. And so at this point, I don't have any other information about x, so I'm going to write out just expressions here for each of my product concentrations. But I do know from my graph, I'm going to go back here, I'm going to see, well, my graph indicates to me that I have 2 moles in 2 liters as my final concentration. So again, I can see, you know, instead here, now I have 2 moles in 2 liters, and that will give me 1 mole per liter as my final concentration. All right, so in order to solve an equation, okay, I need to have only one unknown. And so I know that in this circumstance, I can solve for x because, remember, that 2 plus negative 2x has to equal 1, right? My initial plus my change has to equal my equilibrium concentration. So that's an equation that I can solve. Let me pull that out. So 2, oops. So 2 plus negative 2x has to equal 1. And going ahead and solving for this, I'll let you do the math on this. So 2x is equal to 1. So the value for x is 0.50. That's my value for x. And so knowing that, I can now go ahead and substitute my value for x into both expressions to get my concentration of N2 and of H2. So let me erase some of this. All right, so just to recap, you know, the value of x I came to see as 0.50, and of course that's a quantity in moles per liter. So the concentration of N2 we said was actually equal to x, and so that means the equilibrium concentration N2 happens to be 0.50 moles per liter. Now the concentration of my hydrogen gas was actually represented as 3x, and so that's going to be, of course, 3 times 0.50, which will give me 1.5 moles per liter. Now, last but not least, what I need to do is I need to graph this, you know, the concentration of each species on the graph here that's provided. So, but I need to remember that the values that I have, this 0.50, that's moles per liter, and the 1.5 is moles per liter of my H2. And so what I need to remember is that I really just want the amount of each. Okay, so the amount of N2 is actually going to be 1.0 moles, right? Because if I have 2 liters, then that means I'm going to be doubling the amount of moles that I have per liter. And so the amount of H2 that I have is going to be 3.0 moles. So going ahead and graphing this, I'm actually going to use blue for my H2. So I'm going to start with that. I'm going to start out with 0 H2. And I'm going to end up with, at equilibrium, let me just draw in a little dotted line to kind of estimate where the equilibrium is established. I know that at equilibrium I should have 3 moles per liter, so I need to somehow manage to get up to here, up to this point. And so if I do that, there we go. And so continuing on, trying to be quasi-flat here, you know, that represents the amount of H2 that I have. I'm going to use red to represent the equilibrium amount of my N2. So again, I'm going to start down here with 0 N2. And then I have to find my way up to 1. So if the equilibrium is established here, getting to 1, I'm going to up here, and then carrying on flat. So there is my equilibrium amount of N2. All right, so here's our third example. And so I would like you to try to do this question on your own. Try to see what it is that you're able to do to solve it. And if you're stuck, then feel free to resume the video or and watch me solve it for you. All right, so example number 3. In a gaseous reaction system, we have 2 moles of H2 added to 2 moles of iodine in a rigid 2-liter container. Now the temperature doesn't really matter too much. It's just there because the equilibrium position will change depending on the temperature of the system. So at equilibrium, the system contains 0.04 moles of H2. Determine the equilibrium concentration of I2 and HI. And so the HI is kind of there. I want you to figure out why that's there. So pause the video now, try the question, and then resume the video when you are prepared. Okay, so this is a question that calls for an ice box in order to make the best kind of decisions about our equilibrium system. So I'm going to set that up just really quickly. So it looks like I'm starting off with some H2, and I'm going to react with some I2. And to me, when I react these, this is just a simple synthesis reaction. I'm going to produce some HI. Now I need to remember to balance this, so I'm going to add a coefficient of 2 along with my HI. All right, so now let me work on my ice box, so ICE. So now on the side here, I know that I have the quantities that I have of each of my reactants are moles in 2 liters. So in order to get my molar concentration, I'm going to divide those values by 2, right? So for instance, if I have 0.200 moles in 2 liters, that will give me 0.100 moles per liter. Sorry for squashing that in there. So let me fill that in. So I'm going to start off with 0.100 and 0.100. And I'm going to assume that initially, unless you're told otherwise, assume that you have 0 moles per liter of any products. And so let's write out what the change is. So I know the amount of H2 that I have is going to decrease by X. And likewise, due to mole ratios, I should experience the same change in the concentration of my I2, my iodine. I'm going to expect that all of those hydrogen and iodine atoms are going to join to make HI, so the amount of HI should increase by 2x. All right, now let's look at what other information is given to me in this problem. It tells me that at equilibrium, I have 0.40 moles of H2. But remember, that's in 2 liters. So I'm going to have to divide the amount of H2 that I have by 2, and that will give me 0.020 moles per liter. So now in this question, it's quite simple. I know that, my initial plus my change will equal out my equilibrium concentration. And so by looking at this, I can use this whole complete equation to solve for X. Though, it doesn't, at this point, hopefully you've realized that the amount of I2 also has to be 0.020, just due to the math here. But let's just go through the motions. So I'm going to pull this equation out here. 0.100 minus X equals 0.020. So X, isolating X, 0.100 minus 0.020 will give me a value for X of 0.080, and that's of course in moles per liter. And so that allows me to figure out my concentration of HI. So I've already quasi sort of determined the concentration of my I2. So let's write that out. So the concentration of I2 also has to be 0.020 moles per liter. But my concentration of HI is given by the expression 2x. So 2x means 2 times whatever x is, 0.080 moles per liter, which gives me 0.160 moles per liter. And I'm done. Hopefully you did okay with those questions. I'm going to suggest some practice questions for you to attempt for homework, just to solidify some of these ideas. Be sure to arrive to class next time with some questions in hand in case you need some clarification.